Hi everybody. Hey, I'm Dr. Kennedy and this is our first lecture together in 2110 this fall. So this lecture is going to be on energy and enzymes and the introduction to cellular metabolism. This is some really fun stuff here. So what exactly is metabolism? All right, so metabolism. This is the sum of all chemical reactions required for life. And basically metabolism has three different purposes. One, it's going to extract energy from the environment. Two, we're going to take down and we're going to break down organic molecules that we get like glucose and fats and proteins. Not only are we going to extract energy from them, but we're going to use those breakdown products, those intermediates, as building blocks to make larger molecules. And of course, the third thing that we're going to do for metabolism is eliminate waste. And we're not going to discuss that here in this class. But what we are going to talk about are these chemical reactions and how we extract energy from these chemical reactions. And on the right, you can see a metabolic chart of cells. And what's very interesting, look through the middle of it. You'll see this thing that says glucose, glucose 6P, fructose, GAD, and then it goes right into a little circle. That is cellular respiration. That line is glycolysis, and then the little circle there at the end of it, that's Krebs cycle, or the citric acid cycle. And the first thing you realize, cellular respiration is at the heart of cellular metabolism. Both anabolic processes, which is building things up, and catabolic processes, which is breaking things down. Now, that's a simplified version of a cellular respiration and also a simplified version of metabolic pathways inside of a cell. Yeah, That is actually a much more accurate representation of the chemical reactions that take place in a cell every second of every day of your life. It's amazing. And you look at this and you're just like, your mind is blown away, or at least mine is, because every line represents a chemical reaction. Every little dot in there represents an intermediate. And you realize two things here. And that first thing is there are a lot of chemical reactions in life. I mean, we'll talk about what life is here in a second. But, this is the sum effort of hundreds, thousands of scientists working over decades of their life and culminates in over 100 years worth of information, 100 years worth of knowledge combined into that single chart. And to me, the fact that we know so much about cells is astounding. And one thing in these intro biology classes, we often we talk like this is how it works and this is everything that we know, and there is still so much that we do not know about cellular metabolism. So, metabolism is important for life, and to really understand the importance of cellular metabolism, it's good to know what does it mean to be living. So let me ask you a question, and you might want to pause this video for just a second. How would you define life? How would you describe it? How would you recognize something as being living? And that's important because it puts why we want to study metabolism and chemical reactions and cellular respiration, and of course my favorite, chemiosmosis, why we put all of that into our introductory biology classes. So what is life? Or what does life do? You could ask me, you could ask Dr. Hawken, you could go ask a bunch of different scientists, you could go Google an answer, you can read it in your textbook. Not everybody agrees on the exact definition of life, but I tend to think of life as an action. Life is a verb. Life does something. And here's a definition I like to use, is that life is an emergent property of a complex system. And of course, at the basic unit of life is the cell. That is the system surrounded by a cellular membrane. That's the boundary of our system. And then we have all of these chemical reactions that take place inside of cells, and they use energy to create order and maintain homeostasis. So you see a couple things here, or several things, not just a couple. Life is an emergent property. We're greater than the sum of our parts. Life needs energy. And it's through these chemical reactions that life emerges. So metabolism, which is the sum of all these chemical reactions of life, well, that's where life emerges from, our metabolism, right? And in fact, for anybody interested in the origins of life, a lot of people believe in the metabolic theory first. Metabolism came before reproduction and evolution. And it's one of my favorite theories of the origins of life. It's not the RNA world theory. So as you start to realize, life needs energy, and we get our energy from sunlight. In fact, the vast majority of life on this planet gets its energy from sunlight, and plants through photosynthesis. What they do is they take the energy in sunlight and they transform that energy and store it as chemical energy and glucose and other carbohydrate molecules. And then plants and animals and most life, once they take that energy and carbohydrates, they break it down, they extract the energy from these high energy organic molecules, and then they make ATP out of it, and that's the subject of cellular respiration. And in fact, ATP is the energy currency of life. It's pretty amazing that all life makes ATP for energy. Okay, getting used to doing lectures like this here. Okay, so you and I, and all animals, are heterotrophs, including this praying mantis, which is eating an assassin bug. So that praying mantis is actually higher up in the food chain or food web than a cheetah. Wild, isn't it? And the other one hanging by one limb is a robber fly eating another smaller fly. They're very these are amazing predators. But they're heterotrophs. Troph means feeding, hetero means other. So what these heterotrophs are doing, like you and I, we eat. That is our source of energy. We ingest our food, we break it down, we transfer that energy to ATP, then our cells can use ATP to do work. And basically, even plants do this. Like I said, even plants break down carbohydrates to make ATP. So you start to see that energy is really important to life. Without energy, there is no life, right? Energy flows through life. And in fact, we cannot recycle energy at all. We have to have it constantly flowing through this. And, we've known about energy for a long time. But interestingly, back in the early 1800s, late 1700s, there were some people doing these experiments with dead animals, and they would zap them, right? They would take this little prod with electricity, zap a dead frog, and the muscles would twitch, twitch like this. And they're like, whoa, maybe we can reanimate life with energy. And in 1818, Mary Shelley, of course, wrote Frankenstein, or the modern Prometheus. And it had this in it. It was the first work of science fiction, basically. And it spawned an entire genre of science fiction and horror. And a lot of these like Frankenstein monster movies revolve around using energy to reanimate life. Now, that being said, you can't reanimate life for that pesky second law of thermodynamics, but energy is one of the secrets to life. Without energy, there is no life. And in fact, if you cut life off from energy, life dies. We return to equilibrium. So you never want to be in equilibrium. So the question now is, what is energy? And this is important, right? Because if we're going to say that life needs energy and we're doing all these chemical reactions of our metabolism to extract energy, then what is energy? Okay, so first of all, we know we need it, but energy is the ability to do work. Earlier I said life is a verb. Life is an action. Life does something. Well, in many ways, energy is the same way. Life can affect change on the universe. So we often define energy as the ability to do work. Now, my favorite thing is, well, what is work? And some people what work is, and you might say, oh yeah, that's something I don't like to do. But there's actually a scientific definition of work. And basically it's the ability to move an object through a certain distance at a certain speed. And that is doing work. So for those of you that have ever worked out in the gym, I used to work out all the time. I cannot wait to get back into the gym and start working out once again. But if you're bench pressing, if you're curling, you are doing work. You are using energy to move an object through space. And the ability to do work, that is Gibbs free energy. So the energy available to do work is Gibbs free energy, and we call that delta G. Now, hold on to that delta G because we're going to come back to that in a little bit. Now, I want to take a minute here, and I'm just going to sidetrack a little bit, go on a little bit of a tangent. I know, you can skip this part if you want, but I enjoy kind of like going on tangents and expanding our knowledge base a little bit. And let's talk a little bit more about Einstein and energy here. we defined it as the ability to do work. Well, at least Gibbs free energy is the ability to do work. In 1905, this German patent clerk named Albert Einstein published perhaps the most famous equation in the world. E equals mc squared. That means energy is equivalent to the mass of an object times the velocity of the speed of light squared. This equation revolutionized our world. Think about that. Energy equals mass times the speed of light squared. The speed of light, for all of those that you're interested, is 186,282 miles per second. You could go around the Earth 7.5 times in 1 second at the speed of light. And what Einstein realized is that the mass of objects has energy. That's crazy. That means that energy and mass are interconvertible. And this, of course, this revelation did several things. And one of them, it brought in the atomic age, because scientists realized that there was an enormous amount of energy tied up in the mass of objects. And if you could split an atom, you could release enormous amounts of energy. And in fact, that's exactly what a nuclear bomb does, is that it releases enormous amounts of energy by splitting the atom and converting some of the mass to energy. And in fact, in that bomb explosion right there, approximately 1 gram of matter, 1 gram, is turned in to pure energy. So there is an enormous amount of it. The other implication for that in physics is that it set the speed of light as the fastest you can go in the universe. In fact, no objects of mass, no objects of matter can go the speed limit, because as you go faster and faster and faster, it requires more and more energy to continually accelerate you. And as you approach the speed of light, the amount of energy it takes to keep accelerating you approaches infinity. So it takes an infinite amount of energy to accelerate you past the speed of light. And in our everyday world, it has implications, actually. You can walk pretty easily a mile. Jog a mile, well, if you're like me, I don't really like jogging. I could do it. I'd be sucking wind, but I'd get there quicker. Sprint a mile. Yeah, good luck. Only extreme athletes can sprint a mile, because to move yourself faster requires more energy than to go slowly. That's why you, as you speed, if you go too fast, if you're going 75 versus 55 on the interstate, you burn more gasoline to get to the same place, because it takes more energy to go faster. So that's kind of the implications of E equals mc squared. And Einstein never got a Nobel Prize for that. Interesting, huh? So we know what energy is now. Now, energy is governed by these laws of thermodynamics. They were developed in the 1800s when we were studying steam engines. And there are 4 laws of thermodynamics. You need to know 2. Oh, getting the camera right there, Tom. There are 2 laws. The first law, energy cannot be created nor destroyed. That means if you have a closed system would be like the universe, where nothing gets in, nothing gets out. You have a boundary that is impermeable. That closed system, you're never going to lose energy. You're always going to have the same amount of energy in a closed system. You can't create energy. You can't destroy it. That sounds great, right? We're all safe. Now, the second law of thermodynamics, this is like a sucker punch of nature, right? Like, nature really got us on this one. It says that every time you use energy, if I'm using my free energy to throw a ball, or I'm using free energy and I'm releasing energy and stored in chemicals, every single time I use energy, I transfer it from one object to another, or I transform it from one type to another, I increase entropy in the universe, okay? Which means that I'm losing free energy. That means I'm losing delta G. We're losing it. And that change in entropy, that is our delta S. So entropy in a closed system is always, always increasing. Okay. So now that we know that the laws of thermodynamics govern energy transformations, you may have realized that energy comes in different forms. There's just not free energy. There's these different forms of energy. And you may already be familiar with these. And in broad terms, there are 2 forms of energy. There's kinetic energy, which is the energy of motion. And then there's potential energy. And potential energy is energy that is stored. So let's take a look at kinetic energy first. So kinetic energy is the energy of motion, and there's lots of different forms of kinetic energy. One of those that we're really familiar with is electrostatic discharges and electricity. So an electrostatic discharge, in the wintertime when you go and you zap your sibling or a friend, you drag your feet across a carpet and you can zap somebody. What you're doing is you're actually gaining electrons. You're ripping electrons off the surface of the floor. You're becoming negatively charged. You go up to somebody and zap them. You have a little electrostatic discharge. That's a movement of electrons, and that's electricity. Electricity is a movement of electrons. And of course, a very large electrostatic discharge is lightning, or if you're Emperor Palpatine, from Star Wars, you can also unleash some force lightning. I assume that that's something. I've always liked it. It looks like lightning to me. Probably some type of kinetic energy, right? Another form of kinetic energy that we are all really familiar with is electromagnetic radiation. So think about it this way. You're watching the computer screen right now. It's emitting light. And that's one tiny fraction of the entire electromagnetic spectrum. And what's happening here is you get these little packets of energy. They're called photons. And they move in waves. And those wavelengths determine the amount of energy the photons have. So if you've got a really short wavelength, okay, you have more energy. And longer wavelengths have less energy. So violet light has more energy than red light. That's why we fear ultraviolet light, because ultraviolet light has enough energy to damage our cells. Whereas infrared, we can't see it, and it really can't hurt you too much. And then the wavelengths of light coming out of your cell phones are microwaves, and they basically don't have enough energy to cause any type of cellular damage. And of course, there's thermal energy. The universe is made up of atoms, right? And we know that atoms are made up of protons, neutrons, and electrons, but atoms are where it's at, right? And these atoms like hydrogen, carbon, nitrogen, oxygen, they come together to form molecules. But the point that I'm making is that at this molecular level, these things have energy. They're vibrating, and that's the thermal energy. And all matter in the universe has at least some thermal energy, because if you didn't have thermal energy, you would actually have zero entropy, and based on the laws of thermodynamics, you can't have zero entropy, so you have at least a little bit of this thermal energy. And we measure thermal energy as temperature. So the temperature of a system is the average thermal energy of all the molecules in that system. And we measure that as either Fahrenheit or Celsius or Kelvin. And I got a controlled burn in this image, and that controlled burn is the fire is you can feel the heat, and that's creating thermal energy when you feel it on you. You can feel it increasing the kinetic energy of the molecules. Okay. Oh, by the way, anybody interested in fire? We hear a lot about fire in the press. It's really bad because it wipes out our forests. But the reality is a lot of our western forests and southeastern forests actually depend on fire as part of their natural cycles. Now let's move to potential energy. Does that pizza look good? Looks good to me. I just ate, so I'm not that hungry right now, but I usually get pretty hungry when I lecture because I like to eat after lectures. Pizza. Man, I can just... Oh, yeah. Awesome stuff. It's one of my favorite foods. Pizza, fish, with anything with green chilies. Awesome. But the reason why I talk about it is we eat food. And of course, I don't know about you, but I subside on pizza quite a bit. Probably more than I should. At any rate, pizza has carbohydrates in the crust. It's got fats in the cheeses. It's got proteins. And all of these organic molecules basically store potential energy, and specifically they store it in the bonds, in the covalent bonds, and they store it as chemical energy. So chemical energy is a type of potential energy. Different bonds, different covalent bonds store more potential energy than other covalent bonds. And that's a point I'll come back to here in a second. So of course, here is a glucose molecule, and if you're drinking soft drinks, yummy Mountain Dew, sweet nectar, right? I had to switch to Diet Mountain Dew. Stuff is addictive. Don't get started on it. Okay, I'm back. Yes, the lighting looks different, and I'm dressed differently. That's because I had to take a pause in the recording here today, and we'll find more out about that as time goes on. But we now know that there are these two forms of energy, right? We've got kinetic energy and we've got potential energy. And we know from the laws of thermodynamics that energy can be transferred and it can be transformed. So look at this coal burning, right? So what's happening is you've got energy stored in the molecular bonds, the bonds holding all the carbons together and holding the carbons and the hydrogens together. And as that bonds are being broken and forming new bonds of carbon dioxide and water, basically this reaction, this chemical reaction, is transforming chemical energy into kinetic energy. And specifically, the kinetic energy that is forming is electromagnetic radiation. And we can see it as light, that's the light in the flame. And we can also feel the infrared as heat on our skin. So that's kind of cool that this is an interesting energy transformation. And of course, the energy transformation is increasing entropy. So let's go a little bit into this energy transformations here. You know that like when a solute diffuses across a membrane, if you've got more solutes on one side of the membrane, more solutes on one side of the membrane than the other, your system is out of equilibrium. Delta G, which is your free energy, is less than 0, which means that you have energy available to do work. Now, as a solute diffuses down its concentration gradient, cells harness that to do work until eventually you reach equilibrium. And in equilibrium, of course, delta G, the free energy, equals 0, and you have no more free energy available to do work. So a system in equilibrium also has a high state of entropy, and entropy is that delta S. So that's our measure of disorder, right? So the amount of total energy hasn't changed, but our entropy has increased, and our delta G, which is our free energy, has certainly gone down. Now, let's take a closer look at this. A little bit more about thermodynamics. I've always found thermodynamics to be really interesting. You've got these closed systems, and in a closed system, let me define what a system is. A system is all these interacting parts surrounded by a boundary. So you could imagine a cell as all of these chemical reactions taking place and all the interactions of the cell, endomembrane system and the cytoplasm and of course the cytoskeleton. All these things are working together within a set boundary, which is our cell membrane. That is our system. Now, a closed system means that nothing is entering, nothing is leaving, and closed systems always go to equilibrium. Whereas an open system has things that come and go. They're not closed off to the rest of the universe. So this is interesting. Here's a closed system here. Initially, all closed systems have a delta G less than 0, which means they have energy available to do work. But eventually, closed systems all go to 0. Delta G equals 0. They all go to equilibrium. Haven't lost any energy, but the energy's been degraded as as they reach equilibrium and entropy increases. Now, open systems have a constant supply of energy. Energy flows through open systems. You can still have your boundary, like that of a cell membrane, forming the boundary of our cellular system, but energy and materials can flow through this system, and that way you have a constant supply of energy. You always have a delta G less than 0. You can always do work. And of course, our Earth is an open system. We have a constant supply of sunlight always coming into the Earth. And the Earth is not the only open system. And in fact, most things in the universe are actually open systems. And of course, life is an open system. And this is a snowy egret. It was really posing for me when I was kayaking a few years ago. But the snowy egret is a bird, is a living organism. It is also a system made up of many cells, and it is an open system with a constant supply of energy. And that's important because if you cut life off from energy, as I said earlier, life dies. Life will decay toward equilibrium. So remember when I said that life is a complex system, but life is an emergent property of a complex system. And that complex system is all these chemical reactions taking place, right? So life is this emergent property of a whole bunch of chemical reactions. So life gets energy from chemical reactions. I mean, you can't just use any form of energy for life. I mean, think about this. You could take your pizza or a jar of peanut butter, throw it in the microwave, and zap it in the microwave. You're not going to get something living out of that. And the reason why is, well, you can't use that energy. That input of energy could just as easily break down a molecule, an organic molecule, into something simpler as it would build something up. So metabolism is this very complex set of chemical equations that I showed you in the very beginning of this lecture. But the point here is that life extracts energy by chemical reactions. Now, life can also extract energy as an autotroph from sources of electrons and sunlight. And we'll talk about photosynthesis later in the semester. But for right now, let's talk about heterotrophs and how we get our energy stored in covalent bonds. You see, the energy stored in a covalent bond, that's chemical energy, that's stored in the bonds that hold molecules together, is a function of the position of the electrons relative to the nucleus. Let me say this again. Electrons, electron, electricity, electric, you kind of get the idea here, right? Energy. So electrons have energy, and the further away they are from a nucleus, the more energy they have. So if you have a nonpolar covalent bond, like the one between two carbon atoms, or between carbon and hydrogen, those electrons are equidistant from the nucleus. They're as far away from the nucleus as they can. Those bonds hold lots of energy. And then as we get different types of covalent bonds, as we go from nonpolar covalent bonds to polar covalent bonds, those bonds store less energy. So if you have a polar covalent bond with oxygen and carbon, or oxygen and hydrogen, those bonds do not store a lot of energy because the oxygen is electronegative. It's holding on to those electrons very tightly. So think about this. Gasoline, right? Gasoline is octane, or it's got a lot of octane in it anyways. There's other stuff, but octane is 8 carbons. Oh boy, it's like 18 hydrogens, right? It's a hydrocarbon. It's just all carbon and hydrogen. Lots of energy. Don't light a match around gasoline, right? Because if you light a match around gasoline, it's got lots of potential energy. Those bonds are very easily broken, and they rapidly break and form carbon dioxide and water, releasing enormous amounts of energy. And all it takes is a tiny little spark to release that. They're the same match in water, and nothing happens. It goes out. It's like the most brutal thing of all. Nothing, right? And when it goes out, that's because the flame of the match just doesn't have enough energy to break the bonds holding a water molecule together. Okay, so one of the things about these molecules that store energy is that we can actually talk about the total energy in a molecule as the enthalpy, and that is H. Think about this. We've talked about delta G, we've talked about delta S, and now we've talked about H. Seems like we're building towards something here. Maybe. Hold on to those variables. We're going to come back to them. But here's one more thing that I just want to show you really quick. And this is kind of interesting. And this just goes to show that when we talk about the potential energy stored in molecules, that really has a lot to do with the electrons. And these electrons, you know, they can be in these different distances from the nucleus. And this is showing that as electrons move further and further away from the nucleus, they have more potential energy. And when we talk about something called a redox reaction in section 8.2, and when we talk about redox reactions in the next section, the next lecture basically, that position of the electrons becomes really important for energy release during those redox reactions and the transfer of energy in redox reactions. So that's another thing that you want to keep in mind here that we'll learn about in the next section. But let's move on here. I also want to talk a little bit about chemical reactions. You know, life is an emergent property of a complex series of chemical reactions. So just to remind you what a chemical reaction is, chemical reactions make and break bonds. And there's a couple things you need to know. First of all, it takes energy to break a bond. Any bond, it takes a little bit of energy. That is why the paper on your desk does not spontaneously combust. And no matter what you've seen on the internet, you will never spontaneously combust. I promise you. You cannot do that. And the reason why I know that is because it takes energy to break a chemical bond. Okay, so you're looking at this fire and you're like, well, fire's releasing energy. You know, you break a pencil, right? And you hear it snap and you're like, oh, well, energy's released when it breaks. Okay, so we often think that energy is released when chemical bonds break. That's not entirely true. It takes energy to break a bond. But if you're breaking a bond, like in a glucose molecule, C6H12O6, bunch of covalent bonds there, and you break the bond and immediately form new bonds to form the products of carbon dioxide and water, that's where your energy is released, right? When you form carbon dioxide, when that carbon goes from being bound to carbons and other hydrogens to being bound to oxygen and carbon dioxide, that is where your energy is released. So, it takes energy to break a bond. Energy is released when bonds are formed. And one other thing, I think you guys have all had chemistry, you know this, chemical reactions do not create nor change the elements. It rearranges your elements into different molecules. So you start out with your molecules of your product, and you have different molecules, you start with molecules of your reactants, and then you have different molecules in your products. But you're not changing elements. That's why chemical reactions are always balanced, right? If I've got 6 carbons in my reactants, I better have 6 carbons in my products. So that's why whenever we write an equation for cellular respiration, and it's C6H12O6 plus 6O2, well, you got 6 carbons in your glucose molecule. That's why you make 6 carbon dioxides, right? Because each carbon dioxide has one carbon atom, and you have to have 6 of them. Okay. Now here's another thing. We know a couple things about these chemical reactions, right? So we're using some energy to break them, break the bonds. We rearrange them to create new molecules, and then some energy is released when the new bonds are formed. Okay, so chemical reactions in life also involve energy transformations, right? So we have these different types of chemical reactions. You can have exothermic. These release heat. You burn a fire. That's an exothermic reaction. Delta G is less than 0. We also have something called an exergonic reaction, and these are spontaneous reactions. That means delta G is once again less than 0. But an exergonic reaction is very similar to an exothermic reaction, except exergonic reactions don't always have to release heat. That's the difference. And they're called spontaneous. Okay, spontaneous in chemistry and spontaneous in your lives are probably different. To you, spontaneous is you do something randomly. Oh, you can't see it. I'm not in class anymore. I used to throw a piece of chalk across a room or something like that spontaneously to represent spontaneous in our life. I just threw a bottle cap. Bottle cap? Yeah. Mountain Dew cap. Mountain Dew cap. I just threw it across the room there. Yeah, that was spontaneous. But in chemistry, it's different. A spontaneous reaction, to break the bonds to get it started, you still have to have your activation energy. But, like, if I'm burning wood or gasoline or whatever, not only are these exothermic reactions releasing energy, but the energy released when I break a glucose molecule, and then when I form carbon dioxide and water, the energy released when I form the products of carbon dioxide and water is enough to break the bonds holding their reactants together. So these reactions will continue on until they run out of fuel. That's why they're called spontaneous. And then the other type is an endothermic reaction that takes in heat. And you also have endergonic reactions, which are non-spontaneous reactions. Both of these are delta G is greater than 0. Think anabolic reactions, right? I'm going to take some carbon dioxide. I'm going to take some water. And you know what? To make a glucose molecule out of that, you must add in energy. I could have carbon dioxide and water floating around in a jar like this. This is my tea right here. Yes, I really drink 1.5 liters of tea at a time. This is chai tea. I love it. I'm trying to get off of this stuff right here. Oh, you can barely see it. Diet Mountain Dew. So I'm trying to drink this stuff instead. But here's the point. I could fill this jar up with carbon dioxide and water, and I will never, until the end of time, ever get a molecule of glucose unless I add in a sufficient amount of energy to break the bonds holding carbon dioxide and water together and continually add energy to build up a glucose molecule. And that is why something like photosynthesis requires an input of energy. Okay, now let's move on here. We're talking about chemical reactions and how they involve energy transformations. There's an equation that you need to know. It's a standard equation for free energy. And this came up by a guy named Willard Gibbs, who in 1903, Einstein of all people, said this was the smartest American scientist. And he was instrumental in our development of our understanding of thermodynamics. But Willard Gibbs came up with this free energy equation, and we've already seen it. Delta G, you should be thinking to yourself, that's free energy, that's the energy to do work, equals delta H, which is the change. That's what delta means, change in enthalpy. That's the amount of energy content in a molecule minus the temperature times the change in entropy. So let's take a closer look here. There's your delta G, free energy. Remember, if delta G is less than 0, then you have energy to do work. Your delta H is your change in enthalpy, which is a change in, they measure that in the heat content of a molecule. And delta S is your change in entropy. And then T is temperature. Now, you and I, we most likely think in terms of Fahrenheit. That T for temperature is in Kelvin, okay? Which 0 is absolute 0 with no entropy, which we can't actually have. And then room temperatures are like around 276 degree Kelvin. So here we go. We have fire. And what we see here is a change in enthalpy. Important that the delta S, that change in entropy, when the products are less ordered than the reactants, then delta S is greater than 0. And we're going to get that exothermic reaction. Okay. And also the amount of free energy released is also a really big function of temperature. So the higher the temperature, the more impact that entropy is going to have. Now let me explain this entropy one more time here for you. It's measured disorder. And if you notice, I got a picture of like burning some newspaper or something. Okay, the newspaper has print on it, right? And these prints have letters which are in a specific sequence that convey words. Those words convey information. It's ordered, low entropy. As I burn it, delta S, the entropy increases. I could collect every carbon dioxide molecule, every water molecule, every piece of that soot and stuff that didn't completely combust, put it back together again, and I can never, ever recreate that information. It's gone forever. That is the information loss of delta S. That is your increase in entropy, your increase in disorder. Okay? So if you think about like a glucose molecule, C6H12O6, there are 24 atoms that come together to form that molecule. And that's more ordered, right? That's a more complex molecule than carbon dioxide or water. Carbon dioxide is just three atoms, right? It's two oxygens attached to a single carbon atom, and water is two hydrogens attached to an oxygen. It's much more simpler. It's way less ordered than your molecule of glucose, and that's part of the reason how you know that delta S is increasing. And as a result, what that's going to do is give off free energy. Okay. So, of course, we know free energy is energy that can do work. And the higher the temperature, entropy has more of an effect on free energy, because our equation is delta G, which is our change in free energy, equals a change in the enthalpy, like how much heat is giving off, minus a change in temperature times the change of entropy. So as temperature goes up, it's going to have more and more of an effect. As temperature goes down, like if you had something that's very cold like ice, then entropy is going to have a very small effect on your change in free energy. And that's why you can have an exergonic reaction that's not necessarily exothermic. Okay. And then, of course, you can have an exergonic reaction that's also highly exothermic, just giving off lots of energy like this fire. Okay. So, as I said earlier, exergonic reactions, they are spontaneous. So this is the equation, once again, for cellular respiration. You'll want to know that well for the next test, because this reaction is spontaneous. And the reason why is because when the products of carbon dioxide and water are formed, they release enough energy to break the bonds holding the reactants together. Now, we're going to talk more about that in section 8.2, exactly where that energy is coming from, how that electromagnetic radiation is released. And to me, that's really, really interesting. Okay, And then this goes to show an exergonic reaction. And if you notice, if you look at this chart, the energy in the reactants is more than the energy of the products, and the energy released, the Gibbs free energy, which is delta G, is the energy in the reactants minus the energy in the products. Now, you notice that hump, that is your activation energy. That is like if you take a match to light something on fire. That is the activation energy. It does not affect your Gibbs free energy. And that activation energy is also why you will never spontaneously combust, because you have an energy barrier to breaking those down. And then when we talk about enzymes, at the end of this chapter, we'll talk about how enzymes lower that activation energy to help catalyze reactions. Well, our metabolism is not just about breaking down lipids and carbohydrates and proteins, right, and extracting energy from them. Life depends also on endergonic reactions. And often these are anabolic reactions where they're building something. They're taking these small building blocks and they're building something more complex with them. And just like if you were taking your Legos, right, you're going to build the Lego Millennium Falcon. How much I'd love to have the Millennium Falcon, the Lego Millennium Falcon. That would just be so awesome. But to build your Lego ship requires an input of energy. Anytime you build something, you're requiring an input of energy. One of the most important endergonic reactions is photosynthesis. Photo means light, synthesis, synth means put together. So what plants do is they take carbon dioxide and water and the energy of sunlight, and they are able to build carbohydrates with that, and that is the products. And in this case, the products are more ordered than the reactants. And because they're more ordered than the reactants, you have to have an input of energy. You could never get carbon dioxide and water to ever move around without any input of energy and form carbohydrates. It just won't ever happen. The second law of thermodynamics stops that from happening. So here's my picture of a leaf showing a non-spontaneous reaction. It's called non-spontaneous because, it takes a lot of energy to break the bonds of carbon dioxide and water. I mean, those are really, really strong bonds. I mean, oxygen is holding onto these electrons. It takes a lot of energy to break them, and the energy formed when the carbohydrates are formed is nowhere near enough to break the bonds of the reactants. And of course, when you're doing an endergonic reaction, the products store more potential energy than the reactants. And now you start to see why life needs a constant supply of energy, right? Because we're creating order. Life creates order. Energy flows through life to create order. And as a result, we're this emergent property of a complex system. Is kind of cool. Okay, now, last thing about chemical reactions here. Two other things affect the rate of chemical reactions: temperature and concentration. Temperature makes sense, right? Temperature is you increase the temperature of a system, things move around faster. There's more kinetic energy. So not only do you increase how much they're interacting with each other because they're moving faster, you also increase the force at which they're hitting with each other. In reality, for things to work, they have to hit just right. But you have to hit just right and just hard enough to break those bonds and form new ones. So temperature can really speed up the rate of a reaction, and so can concentration. So as your system becomes more concentrated, what happens is the concentration also increases your rate of encounter, which speeds up your reaction rates. And those two things work together to speed up reactions. And then, as we're going to learn later in this chapter, it's not just temperature and concentrations that are important too, but we also have enzymes that will speed up the rate of reactions. And enzymes also are very much temperature and concentration dependent as well. Okay, well, that's it for this section 8.1 on the role of energy and enzymes, and I hope you guys learned something from this. Okay, until next time, I'll have my next lecture up soon.